Okay, welcome to the Henstitute. We're going to take this concept that we had with the idea of the magnetic flux. That's what this is, magnetic flux. And the idea of an EMF, electromotive force, which is basically the same thing as saying voltage that would be created across this moving wire here, or this moving beam, and it's normally equal to the change in the magnetic flux divided by time. But what we're going to do with this one is we're going to come up with a different equation. If you notice in this picture that I also have situations in which this object is moving with some velocity and it moves a certain displacement here, and then we have time. And we have time sitting up here at the very top that we also have to kind of look at. And so if I put all those together, we should be able to modify our EMF equation here into a different situation. So if I imagine that I have this beam here, this is some kind of wire, and the idea is it starts out here and it's going to move in this magnetic field. So this is these little X's here are our magnetic field, and they're just indicating that they are moving away from you or into the paper. And then they talk about this little light bulb here, but I'll get to that, and the fact that the light bulb is lit up, which means some kind of voltage is being created across here. So as I move this coil, or not this coil, but this piece of material across this series of wires, these two wires here at the top and at the bottom. So there's a wire at the top, the bottom, they're eventually connected to my light bulb here. But by moving this in this magnetic field, we should create some kind of voltage or EMF across here. So I'm going to show how we can kind of modify this equation. Basically what I'm going to do is I'm going to substitute this equation in for this one. And so what we'll end up with is the electromotive force, so the voltage across there would be the change in BA sine phi all over delta t. Now I'm going to make this a little bit easier. I'm going to assume that my phi is 90 degrees, which is kind of what we have in this picture, where the magnetic field is into the paper, but the wire is being pulled to the right, so they're perpendicular to each other. So that means that the sine is going to be the sine of 90, which is going to be 1. So the sine of phi will just equal 1, and we don't have to worry about it. So that simplifies my equation a little bit into delta BA over delta t. Now I'm going to change this a little bit. Let's assume that our magnetic field is not changing, so I can pull it out of this little delta, but I actually have a change in area. And then the area, if I think about it, I start off with a certain area here, and then the area gets bigger. That's the idea of this. But if I think about this basically being a rectangle, how do I find the area of a rectangle? I really just take the length times the width. So I have this L, which is the distance between these two wires, and then this X distance that we have, but I'm going to change that little X distance. So I'm going to actually write area as L times X here, just to kind of make this a little bit easier. So I'm going to have a B, and then I have a change of XL over delta T. So over here, I have obviously a larger X, but this L is still the same. And so I've created a larger area. So that's where that's coming from. So it's really my X that's changing. So again, I'm going to take this L, I'm going to pull it out to the front. And that's going to write my electromotive force as B times L. And then I have a little delta X. And then all of this is over a delta T. Now the reason I write it like this is I remember delta X over delta T from chapter 2 in our physics 1 class. Delta X over delta T, a change in displacement over a change in time, is just velocity. So the velocity of this particle, or this particle of this beam here, is going to pop into this equation. And so my final iteration of this particular equation becomes that the electromotive force is equal to B times L times V, where this little v is actually the velocity of the beam. So in other words, how fast you're actually moving it through this magnetic field. So this works if we have a constant magnetic field, but we have a changing area because we're actually moving this beam across here. So I've come up with a new way of finding the electromotive force. So I went from a change in magnetic flux all the way into now talking about the magnetic field, the length of the beam, and then the velocity of the beam. We're going to then take this and see how we can actually charge up or get our light bulb to actually run, and what exactly is going on, and what happens if we have loops of wire and things like that. That's what we're going to do as we continue our discussion in electromagnetic induction.